Mhm. Herzlich willkommen Hello and welcome. We still have a little bit time to go before we get started. We just want to do a technical check. Valentin, I saw that you already joined the meeting. Welcome. You are our first speaker, so I would like to do a quick tech check. Let me ask you to unmute yourself.
Here you go. Hello, hello.
Very good. Valentin, I can hear you loud and clear. Welcome to our meetup. We are very happy to have you here. Could you please quickly, just to check, quickly try to share your screen with us so that we see that your screen sharing works?
Yeah, let me just check that I have that I show the slides correctly.
Yeah, just any slide or any screen. Just a technical check.
I need to put it in a new window. Good to do a check. So let me move that here. Sorry, 1 minute.
No problem.
How is that?
Yes, that looks very nice. Yes, I can see the slides and it works perfectly fine. Awesome.
Okay.
Great. Great. Please don't forget that in your settings, I sent you the email that you disable the annotation feature for other people. We had problems in our first meetup, but by disabling that, that shouldn't be a problem.
Okay.
Okay. Thank you very much.
I'll try to find it.
Okay. Don't worry. Don't worry. We will monitor it and we will find it. Okay, Valentin, if it's okay for you, I will mute you for the next, I don't know, 10 minutes or so. No, more 20 minutes. At 5:30, I will do a quick overview about some community news, things that are going on in the Linz IT community. And I think I will be done in 5, 6, 7 minutes or something like this. And then I will ask you to unmute yourself and you can share the screen. And we are looking forward to your talk. Everything okay like that?
Yes.
Great. Awesome. If you need anything, please either go to our Discord server and send a chat message or use the chat of Zoom. We will monitor both chat engines and we can, whenever you need something, we can unmute ourselves and talk to each other. Okay?
Okay.
Good. Thank you. See you later.
See ya.
Matthias, I already saw that you are also in the meeting. Can we do a quick tech check too? I will ask you to unmute yourself. Here we go. Matthias, can you hear me? We can't hear you yet. Maybe you can check your microphone settings.
Okay, now it should work, right?
Yes, yeah, we can hear you. Hello and welcome, welcome. Nice to hear you again. You are our second speaker today, and I would like to do a quick tech check if that's okay for you. Audio is already working, and therefore we can try the screen sharing. Would it be possible for you to quickly share any image, maybe development environment or PowerPoint slides or whatever you have, just to make sure that screen sharing works?
So where is it? I can't find it.
So it's good that we do a tech check. You should see a green share screen button.
Yeah, I see.
Can
it's
you see
right
it?
in the middle. Yeah. And share. Okay.
And nice, nice, works good. I see a slide with a header that really looks very much like the talk you are giving today. So I think we are fine. So with that, I will mute you again and ask you to unmute when we start with your talk. That will be approximately at 6:30 p.m. approximately. If you stay in the meeting, then yeah, everything should be fine. Would you please, when you get started with the presentation, once you start with the presentation, don't forget to disable annotations. I sent you an email where you see where you can do that. Maybe you can try that if it's possible, just to make sure that nobody is drawing things on your screen. Okay?
Okay.
Okay, very good. So thank you and hear you later. Thank you for the tech check. Stefan, bist du da? Okay. Hello and welcome to the third Rust Linz meetup. We are really happy to have you here, and I hope that technology-wise everything works good. You can hear me loud and clear. Video is working. We already did a tech check with our two speakers today, and we are really excited what we will learn in the next 2 hours. Let me give you some quick community news before we go right into the topic with Valentin talking about traits in Rust. First, this meetup is proudly presented by the Coding Club Linz. This is where the organizers mainly come from. And these are the two most important people for today's meetup. It's on the one hand side, Valentin. He will talk about why not to rely on inheritance. And the second speaker today will be Matthias Heiden, who will tell us about how to write kernel drivers with Rust. We are really thrilled to have these two speakers here at our meetup, and we are looking forward to great presentations. As always, we have our own Discord server, the Discord server of the Rust Linz meetup. If you want to join, if you would like to discuss, if you want to ask questions, use the opportunity to get in touch with the speakers, to get in touch with us, to get in touch with like-minded people who are interested in Rust. Join our Discord server and join the discussion. Here you have the invite link. You can pick it up from there, and yeah, you will probably be able to find it. If you cannot write down the link, just go to our website. It is rust-linz.at, and there you will also find a link to our Discord server. Some community use. First one, the Coder Dojo Linz, our very own programming club for kids, is continuously running. We are still in Corona mode, so we are still doing online workshops. Our next online workshop will be tomorrow. If you're interested in the topics, if you have kids, if you know kids who might be interested, here is the link. Here's the link. It's linz.coderdojo.net. We have a very special mini coding contest also going on tomorrow. And if you live near Steyr in Upper Austria, you can also visit an in-person Coder Dojo, which will also happen tomorrow. Second community news, female coders. Our friends at Female Coders, they will do a study group in October. So if you are interested in that, take a look at that. It will be online. And in November, the next study group will be held in person. If everything works out as planned, it will be again in the Wissensturm. For further information, just visit the website of Female Coders or their meetup page. You will find all the topics and links and dates and times there. Next one, it is very the .NET community is very vibrant here in Linz, and therefore the next .NET Stammtisch is also around the corner. The next .NET Stammtisch will happen on the 30th of October, and if I can remember correctly, it will also be an online event. So wherever you live, if you are interested, you can join. Here is the meetup page if you're interested in .NET. This is definitely a meetup that you don't want to miss. Last time, we were telling you about the first cloud native meetup here in Linz. It was a big success, and therefore there is a second cloud native meetup. It will happen at the end of October, on the 27th of October. Don't miss to check out their meetup page to see the next events, to see the next topic, and yeah, visit them. It's a great new meetup, and I think it's a great topic, which is very interesting for a lot of people. Another topic which is relevant for students and for kids in school. In end of October, there will be Digitalferien, digital holidays, something like this, under the motto My Informatics World. This is an event which is organized by Coder Dojo Linz together with Business Upper Austria and the Pädagogische Hochschule in Upper Austria. We will do online meetings on these 3 days for students who have holidays there and maybe who get a little bit bored and who would like to do some coding, get into coding. That will be a very interesting thing. There will be in-person events in certain schools, but it will also be possible to join the Digitalferien via online meetings. So if you are interested, check out the website. You will find more details like the topics and things like that on this website that you currently see here. So this is something offering for students and kids, undergraduate, I would say between 10 and 15 years, something like this. We also have some sponsors news. Microsoft is supporting us in running this Rust meetup. They already had 2 speakers here, and we can always rely on their help. So we are more than happy to tell you about another offering that Microsoft currently has. Microsoft is offering free cloud transformation workshops. If you are interested in topics around modern cloud native development, about Azure and things like that, you should definitely check out this link, aka.ms discover Austria-Azure, and there you will find a list of trainings which are coming up, and maybe you find an interesting topic where you would like to join our friends at Microsoft. And with that, I am through with the community news. Again, I would like to thank you for coming to our meetup, and I would ask Valentin to unmute himself. Let me quickly end my screen sharing. Stop sharing here. Valentin, I can already see your video. Can you hear me already?
Yes.
Yes, and we can hear you too. Valentin, are you ready to go?
I am ready.
Awesome. Then the mic is yours. Please share your screen, and we are looking forward to a very interesting presentation about how to not rely on inheritance. Valentin, the stage is yours.
Okay. Hello, everyone. My name is Valentin Tolmer. I'm working at Google. I've been working a bit with Rust on side projects. It's lots of fun. And
I'm sorry to interrupt you, Valentin. Just to
yes.
be sure that you did that on purpose, your video is disabled. Do you want to disable the video, or was that by accident?
I did
yes,
not want
now
to
we can see
disable
you. Awesome. Sorry to interrupt you. I just wanted to let you know.
Okay, thank you. So yeah, I've been working on with Rust for side projects, and it's an honor and a pleasure to be able to speak at this Rust meetup. Thank you for inviting me. So today I would like to share a very crucial and important feature of Rust, which is, well, you know it already, it's traits. This talk is mainly aimed at Rust beginners with a background in programming, usually with object-oriented languages such as C++, Java, or C#. I'll be mainly talking about Java and C++ as comparison to Rust, but of course that applies to many object-oriented languages. So let's have a look at how we can avoid relying on inheritance, because not everyone has a rich uncle who can conveniently die and leave you a lot of money. How do you get by without inheritance, and how does Rust do it? And yeah, let's dive in. So there are different approaches to the same problem. The core problem that we have is that we want to write generic code. So let's say that we want to manipulate animals, and all animals, at least those that we want to manipulate, make a sound. So if it's a dog, we want it to bark. Otherwise, if it's a cat, we want it to meow. Otherwise, if it's a snake, we want it to hiss, and so on. So we could write code like this: if dog, then bark; else if cat, then meow. But that's very repetitive. You have to list it everywhere that you want them to make a sound. And whenever you add a new type, then suddenly you have to change every call site, because every call site has to handle the new animal. And also, like, if you want to take an animal as parameter, or store it in a collection, or return it, what is the type of a dog or a cat or a snake, or and so on? So you could model that with an enum in Rust, but that's not what we're here to talk about. So let's have a look at how Java does it. So Java, usually you would write an abstract class animal, and you would define a function cry that is what animals do. And then you can create a class cat that extends animal, that inherits from animal, and then implement that function cry. You don't have to do it through an abstract class. You can do, well, you could do it through a concrete class, even though it's usually bad style, or you can do it through an interface, which is a bit like an abstract class, except that it cannot have fields. So to summarize, in Java, you can only inherit from a single class, but you can implement multiple interfaces. The interfaces cannot contain fields, but the classes can. And the interfaces can provide a default implementation for some functions. Okay, now let's have a look at how C++ does it. So this is, again, things that most people know. I'm just laying the ground for what we're going to compare it against. So in C++, you would do a similar thing to Java. You would have a class animal that has a virtual method that is not implemented here. That's the equals 0. And it's abstract only because it has an equals 0 method. And then you would write a class cat that inherits from animal and override the method cry to say when a cat cries, it goes meow. So the thing is, in C++, you do not have a clear boundary between a class, an abstract class, and an interface. So in order to implement multiple interface, you have to have multiple inheritance. Again, because there's no boundary between a class, an abstract class, and an interface. An abstract class is only abstract because it has a function that is not implemented, and an interface is a Java concept that doesn't really translate to C++. So with multiple inheritance, you can even have trouble with a diamond inheritance, where you inherit from two classes that both inherit from the same. So from which path do you get your inheritance from the top one? It can be complex. So that's why people usually recommend composition over inheritance, but that doesn't always work. It has, I mean, there are some drawbacks. Another way that C++ writes generic code is with templates. So for instance, here we have a function make it cry that takes an animal and calls animal.cry. However, here I wrote type name animal, but I could have written type name t and then take a const tref, because it doesn't, the name animal doesn't mean anything there. It's just a name for the type, and we don't have a way to restrict to the interface animal. And actually, you could pass something that's not an animal, but as long as it has the cry method, it would work. So this is what we call duck typing. If it quacks, it's a duck. If it cries, it's an animal. And we don't really know if it's actually what we meant by an animal, but this is how templates work. There's no interface declaration. It's going to come in C++ 20 with concepts, but it's not there yet. And then there's so the templates are doing monomorphization, so meaning they copy paste the function for every type that it's used with, and then inline the type, which makes a different function for every type. There's no one function that handles every type. It's just a copy of that function. Okay, now that the context is set, let's have a look at how Rust does it. So for Rust, we have traits. So a trait, for instance, we can introduce a trait animal that has a function cry. And then if we want to implement a cat, then we declare the cat. This is a struct. It has fields or not, doesn't matter. And then separately from the declaration of the trait and the struct, we say that cat implements animal. So we implement animal for the cat type. And since animal requires you to explicitly define the method cry, we have to say, well, cry for cat does this. So another example, if we have a struct dog that has a name, then if we implement animal for dog, then we can have a different implementation. Say, my name is, Woof. And then that's how a dog will cry. In summary, a Rust trait declares an interface. It's decoupled from the type declaration and from the trait declaration. A type can implement multiple traits. And traits don't have fields. They can only have methods. So it's a little bit like Java interfaces, except that they are used both statically and dynamically. We'll get a bit more into that right now. So how are they used dynamically? For instance, if you want to write the make it cry in Rust, you would say, I take a pointer, like a reference, to an animal. But since animal is not a concrete type, you have to say to a dynamic type that implements animal. So that's what the little din keyword, let me point it, that's what the little din keyword means. And then you can use animal.cry, and because it's a method of animal. And here you only know that it implements the type animal, the trait animal, so you can only use methods of the trait animal. So like in C++, you cannot receive the animal by value because animal is not a concrete type, so you cannot copy it, or you cannot move it. You can just receive it by where it's defined somewhere else. So it has to be by reference or mutable reference or in a box or something like this. In Java, we don't have this problem because every object is a pointer anyway, so we pass pointers everywhere. Okay, now what if I want to return an animal? Let's say I have a barn, and inside that barn there are animals, and I just want to get the first animal. So we have our function getBarnAnimal that takes a barn and return an animal from the barn. So once again, you can see that we're returning a reference to a din animal, meaning we're returning a reference to something that we know implements the trait animal, but that's all we know. I left some blanks in the function definition because if you've played with Rust a little bit, you've ran into this lifetimes. I just wanted to say that here the lifetimes are also relevant because it's a reference that we're taking and returning. So here we're constraining implicitly the lifetime of the return animal to the lifetime of the barn. And yeah, so as in taking arguments, you cannot return a value of an animal. You have to return a reference or a box. Now, what if we want to do static dispatch? So static dispatch is when we know at compile time that we're what is the type that we're manipulating. So for instance, here we're gonna call make it cry on a specific animal. So here T is the type of the animal. We don't know what type it is, but we know for sure it's one concrete specific animal, and we know that it implements the trait animal because we wrote it here. And since we know that it's an animal, we know that we can call cry on it. We cannot access any other methods of T like we would be able to in C++ because we are limited to what the interface animal says. So we can only use methods of the trait. And this is like C++ templates, this is monomorphization. So we're going to make a copy of that function for every animal. So there's going to be make it cry that takes a cat, make it cry that takes a dog, make it cry that takes something else. And here we can take the animal by value because we know the exact type, it's T. So, and make it cry that takes a cat, we know that it's a cat. So we can take a cat by value, we know the type. And yeah, in C++, you can do duck typing and use pretty much anything. So if we want to return an animal, well, it's the same. If we want to, we can return by value. It's okay because we know the type of the animal is the T. So you can return by value. Usually when you do static code, the errors are clear because you know the exact types that are involved. The code is usually faster because instead of having to jump through pointer-to functions, the compiler can optimize and inline the functions. But that could also lead to code bloat because you're copy-pasting the same function for every type that you use it with. So it has its downsides too. But usually it's better to do static dispatch if you can. That's not always possible. For instance, if you have a vector of animals, you cannot have a vector of, well, if you have different types of animals, then you have to store boxes or reference to them. So for static dispatch, you can have a constraint. You can have multiple constraints on the type. So for instance, you can say that T has to be an animal and a runner, so that you can use both cry and run. And you can either specify the constraint when you declare the type argument, or after declaring the function and the return type in the constraints below. It's just syntax, both are equivalent. So how are traits used in Rust? In everyday Rust, you will use some traits, I guarantee you. For instance, one trait that you will most likely use is egg and partial egg. So this is how Rust knows what you mean when you say A equals B. It's because there's an implementation of partial egg that compares the type A and B. So here I've copied a very simplified trait, partial egg. So it has one unimplemented method, which is egg. So for equal, it takes the object and another object of the same type and returns a Boolean, whether it's true or false. And it gives you for free the function NE, not equal, which is by default implemented as the opposite of egg, of equal. And there's some difference between partial egg and egg, being that partial egg can return false if you pass twice the same object, but an egg has to return true if you pass twice the same object. And we say that egg is inherits from partial egg if you want. It has the added constraint that the type has to be partial egg, because it means that to be equal comparable, you have to be at least partially equal comparable. Let's not get too deep into that. It's not critical. So let's implement partial egg for a type. Let's say you have a struct URL and it has lots of fields, different ways to represent the same thing. So you want to say that two URLs are equivalent or equal if they have the same canonical representation. So you will implement partial egg for URL, saying, okay, I take a URL and another. So the self with a capital letter is the type for which we're implementing the trait, so URL. And then returning a Boolean true or false, and we're just going to compare the canonical representation of the two URLs. And that way, once you have written this, you can write everywhere URL A equals you can check if URL A equals URL B. without calling .egg, because the compiler knows that you implemented partial egg, so it can unwrap the equal comparison. Now, I want to talk to you about my favorite trait in Rust, and it's the iterator trait. But for this, I have to introduce the new concept of associated types. So associated types, they will look familiar to C++ template gurus. You want to say the iterator has a next function that returns an option of something. But the option of something, this type is part of the interface. So you have to say what is the type that you're going to return. So item is part of the interface, and when you implement iterator, you have to say what is item. So item, that can be a regular integer, or it can be a reference to a cat, or it can even be a dynamic reference to an animal. Anything goes. But when implementing iterator, you have to say what is the item in addition to implementing next. And iterator comes with many more functions that are defined in terms of next. So when you implement iterator, when you implement just next, you get lots of functionality for free. So let's write an iterator. It's going to be a simple one. It's OK. So we'll create the type always same, and it contains a value. Then we'll implement iterator for always same. Say that the item of the iterator is going to be an integer. And then whenever you call next, we'll just return that integer over and over and over again. So how can we use it? Well, we can create an always same. And this one, I'm creating it with the value 1. So always same is going to be always 1. Then let's print with some debug, which, by the way, uses the debug trait. We'll take, from always 1, we'll take the first 10 items. Because we implemented it so that it never returns none, it's an infinite iterator, so we cannot just say, put everything in a vector. We'll take the first 10 and put that into a vector. We'll collect them, put them into a vector. So when we print this, it gives us 1, 1, 1, 1, 1, 1, 1, and so on. You'll notice that I didn't define the take method for always same. I didn't have to. It's a method from iterator that is defined in terms of next. It just calls next 10 times. So it returns an iterator. It returns a new iterator that will stop after 10 times. OK. Now, let's say that we're receiving a vector of data, a vector of integer, and we want to return an iterator that takes only those small numbers, those are inferior to 3, and it will infinitely loop over them for some reason. My problem is that I cannot write, I don't know what to write for the return type. OK, let's have a look at, let's cut it down and see what we can do. So the iter method on vector returns an std slice iter with item equals i32. Because, well, like here it's integer because it's a vector of integer. In general, it returns an item the same as the vector, what the vector contains. Then we call .filter, which wraps that iterator into a new iterator of type std iter filter. Then we call cycle, which wraps that one into another iterator called cycle. So as a result, the return type of the function should be something along the lines of it's a cycle of a filter of a slice iterator of pointer to animals, sorry, of integers. I should correct the slide. And and then some closure. What is that some closure? Well, if you look back at the type and the filter, it had a closure to check that the numbers were small. And the closure has a specific type because it can do captures, and this type we cannot write. That's a problem, because how do I write my function then? In that case, you can just say it returns some concrete type, unspecified, but what we know about that concrete type is that it implements the type Iterator with that specific item. However, this is still a placeholder for a single concrete type. You cannot return two different types just because they both implement Iterator. Otherwise, you would have to return them by reference to a dynamic object that implements Iterator. Here, it's all static, so there's no vtable involved or anything. It's just a convenience function to say that yes, the type that we're returning, we don't know how to write it, but it implements Iterator. So a question that I often see beginners ask is, why can't I print a vector? Well, vect doesn't implement display. It's a trait. It implements debug, but it doesn't implement display. Well, in that case, I'll just implement it. Well, you can't. Why can't you implement it yourself? Well, if everybody could implement vector themselves, then you could have several implementations that would both be valid, and that would lead to chaos and ruin the utter collapse of civilization. Since we don't want that, Rust has a defense mechanism, and that defense mechanism is the Orphan Rule. So the Orphan Rule states that you can only implement a trait for a type if you either define the trait in your crate or you define the type in your crate. So it means that when you want to implement a trait for a type, you have to own at least one of the two, or both. So you can implement standard traits for your types. For instance, we implemented the standard Iterator trait. Or you can implement your own trait for standard types. You can add methods to vector. But you cannot implement standard traits for standard types. So you cannot implement a trait introduced in another crate for a type introduced in another crate. Okay, is everyone still following? We'll move on to advanced traits. So those are things that you will usually not want to do in your code, but you should know that it exists in case you need it, and it turns out to be the best implementation. So, for instance, you could do some downcasting, which is instance of in Java or dynamic cast in C++. Usually not something that you want to do. It usually means that you don't have the right abstraction. It's possible to do in Rust if you add some boilerplate to the types and so on. It's a bit awkward. Some crates make it easier, but it's still not great. You have to change the definition of the trait. However, there's usually a way to reframe it so that you don't depend on downcasting. So let's say that you're getting an animal. So this is a Java example. You're receiving an animal. You're checking if it's a dog or a cat, then I want to adopt it. And if it's a mosquito, then I want to squash it. Well, so the techniques I'm about to show work also in Java. It's just that in Rust, I want to give you tools when you come around, along this problem to change the way you think and maybe reframe it in a way that is better suited for the tools that Rust gives you. So you could either extend the trait animal and add a function adoptable that by default is true, and then when you implement animal for mosquito, you say that adoptable returns false. Or you could create a new trait. You could say that things can be adoptable. By default, they are. And mosquitoes are not. But you still have to say that that cats are adoptable and dogs are adoptable, and for every animal, you still have to implement adoptable as well, in addition to animal. And your code would look like this. You take a T, and that T is both an animal and adoptable. Since it's both, you can check if it's adoptable. If it's adoptable, then you can pet it, which takes an animal. Otherwise, you can squash it. So some of the traits that I presented so far were you saw them, but you never actually implemented them yourself. For instance, debug, partial egg, or egg. I doubt that you actually implemented them yourself. Usually, they have an obvious implementation, so you would just write, oh, you just derive the implementation from the structure. That way, dog implements debug, partial egg, and egg with the obvious implementations. And usually when every field of a structure implements a trait, you can recursively implement it by calling it recursively on every field. And to generate this implementation with the derived macro, you can actually write your own derived macro for your own traits using procedural macros. I'm not going to get into that because that's a complex topic on its own. Another thing that we kind of touched on with partial egg and egg is operator overloading. To define what the plus does, you just have to implement the trait add for self and the right-hand side, which by default is self. And so we could implement add for cat, say that when we add 2 cats, it returns an integer, and when we add them, like, it returns actually 2. You'll notice that I implemented it for reference of cat and not for cat itself. You could implement it for cat itself, but then you would have to move the value into the plus of the addition operation, and that might not be what you want. So, for instance, here we're adding twice the same value, so we couldn't do that if it was by value. We had to do it by reference. I'll quickly skip over the deref trait because it's not super super important, but basically it's you can specify what it means to dereference a type. So for instance, when you have a man, you can dereference it into 2 kids, and hey, it's just 2 kids in a trench coat. And you can pass a man to a function that that expects 2 kids because the compiler will just dereference it on its own. Okay, so autotrades are traits that contain, so some traits contain no interface and are used just as marker traits. For instance, we saw that egg, in addition to partial egg, was just used as a marker to say, oh, and those types have the strong equality constraint. Some marker traits are automatically implemented by the compiler. For instance, sized just means that we know at compile time the size in memory of your object. You can't make your own auto traits except if you're in Nightly and with some features, but maybe in the future you will be able to. There are some other auto traits that are interesting, like send and sync, but usually you don't have to think about them. So in conclusion, traits are quite different from C++ and Java. They resemble Java's interfaces or C++ abstract class with no fields, but it's not quite the same. Their power comes from the fact that the implementation for a type is separated from both the declaration of the type and the declaration of the trait. So many things in Rust are implemented as traits, and they're very crucial to writing idiomatic Rust. And a very nice advantage of traits is that they're used both dynamically and statically for specifying an interface. So it's the same mechanism for both compile time and runtime. Okay, are there any questions?
Hi, Valentin. Thank you for this presentation. It was very interesting. I did a little bit of work in traits, but I learned a lot of new things. Yes, there are questions, and if that's okay for you, I will relay them to you. Is that okay?
Yes.
Okay, there is one question actually in the organizer team. We asked ourselves, you showed traits in conjunction with structs only. Is it possible to define traits for other types like enums?
Yes, it's possible to define traits for any type, including for an integer. So you can add methods to integer by implementing a trait for them. And of course, it works for enum. You have to be careful whether you're implementing the trait for the enum entirely or for variants of the enum.
Okay, thank you. Thank you very much. The next question comes from Matthias. I will just read it to you. Will we ever get constant iterators? He asks. While and loop can already be used in const functions, but for does not yet work. I suppose that's also because it uses iterators which are not constant. Do you know more about that?
I don't know more about that question. Sorry.
Okay. Okay, yeah. The second thing is also a longer question. I'm not sure if you have Discord open. It's in the Meetups channel. Vladimir is asking, the only difference I know between generics syntax and associated types is that one cannot implement a trait with an associated type multiple times for a type. Are there any other differences? And he brings also an example.
So yes, that's one key concept of associated types. For instance, when you implement iterator for vector, it can only ever return one type. So you don't want to implement iterator of integer for vector and iterator of string for vector, because both don't make sense at the same time. So when you implement, actually you don't implement iterator for vector, but you implement iterator for the iterator type returned by vector, sorry. So if you had generics at the trait level, then you would be able to say iterator of integer for that vector of string, which doesn't make sense. So it's a good point to point out. I guess another key difference is that you can have default values for generics, but I'm not sure that's the case for associated types. I might be wrong. So it's mainly a question of what is the interface that you want to present. Do you want to present an interface that is variable on every trait, or do you want to present a single interface? It's just that you need an extra item, an extra type to be specified.
Okay, thank you very much. The next one is a short one. Christian asks, would it make sense to move all the logic into traits and that classes just hold fields?
Well,
or structs, of course.
Yeah. This is essentially what happens already, because when you add methods to a struct, then you say impl for struct. So you're already doing an implementation block that is separate from the data declaration of what the shape of the struct looks like. It's just that sometimes you want to have some functions that are limited only to a single struct, because it doesn't make sense to have another struct define them. And so you're, in a sense, you could say that you're implementing an anonymous trait just for that struct. So you're declaring that this struct implements an anonymous trait, and that the default impl block is the implementation of that anonymous trait and the interface at the same time.
I didn't look at from that point of view, but yeah, that's an interesting point of view. Yeah, thank you very much. The next one is another question, a short one. You mentioned the diamond problem. I think you mentioned it with C++.
Yeah.
The question is, can the kind of diamond problem also happen with traits?
So yes and no, because the thing is, your traits cannot override the methods of another trait, they're basically, traits are just here for the interface. So if you get the interface from two different traits, it's okay. What the problem in C++ is that in the diamond, the two classes in the middle can implement the class at the top in different ways. In Rust, you can have a diamond trait implementation, if you could say, except that it's not really a diamond. You don't, when a trait inherits from another, it just means that it requires the class that implements it to also implement the super trait. So egg doesn't inherit from partial egg in the way that if you were to somehow just implement egg, you don't get the .egg and .any methods. It's just that to implement egg, you have to implement partial egg. So if you had the same requirements from two traits, it's not a problem. You just have to implement the requirements and implement the two traits.
Yeah, that's clear. I think you described it very well. I could understand it, and I hope the question was answered with that. Let me quickly check whether we have something in the chat. No, I think that chat is empty, and meetups and technical discussion. Yeah, I think you answered all the question. Let me quickly ask the crowd where we have additional questions. This is your last chance to ask your questions live. While people are thinking about it, Valentin, will you be available for questions on the Discord server after your talk for another few minutes?
Sure.
Oh, awesome. Awesome.
I just want to say I'm coming back to the const iterator question. Yeah. So I don't know specifically about const, but something that I didn't mention about the iterator trait is that it's what powers the for loops. So when you say for a in vector, what happens behind is that there's an into iterator trait that turns the vector into an iterator, and then we iterate over that with the .next, and so all of that is just syntactic sugar provided over the iterator trait.
Thank you very much. Thank you for pointing that out. I would like to point out for people who are watching on YouTube, and I know there are some people watching on YouTube there, we don't use the discussion on YouTube. If you want to ask questions, please come to our Discord server and ask your questions there. We will relay them to our speakers. Valentin, I think we are through. I don't have any more open questions. Thank you very much for this great talk. I learned a lot, and I'm pretty sure that it was very interesting for many of our viewers. It was a pleasure having you here, and we hope that you also enjoyed giving this presentation here at the Rust Linz Meetup.
Thank you for inviting me. It was very nice. It was my first time doing a presentation without seeing the audience, so that was interesting. But it was a great opportunity, and thank you very much.
Thank you very much. Thank you, Valentin. Just to notify everybody, we will put, of course, Valentin's talk on YouTube. So in the next few days, we will cut the talk and we will put it on the official Rust YouTube channel. And if you want to rewatch the talk, maybe something was a little bit too fast, or maybe you want to try out some of the code samples that Valentin showed us, you will be able to find the presentations of this week's Rust Meetup on the YouTube channel of the on the official Rust YouTube channel. And with that, I would like to welcome our next speaker on stage. Let me quickly stop. Valentin, you are still sharing your screen. I think you have to stop screen sharing. Thank you very much. And with that, I would ask Matthias to unmute himself. Matthias, can you hear us? And can you let us know whether we can hear you?
Test, test, test.
Yes, it works great. We can hear you. Great.
Awesome.
Are you ready to give us your presentation? We are really all of us are looking forward to these presentations because we are eager to learn how to write a kernel driver. That's really a very interesting topic you started here. Are you ready to get started?
Yeah.
Awesome. Then the stage is yours. Do you want to turn on your video, or will you keep your video turned off?
Yeah, one moment.
Yep. It would be very nice to see you. Yeah, nice. We see you. Okay,
So,
Matthias, again, thank you for being here. Thank you for taking the time and sharing your findings with us. The stage is yours.
thanks. Thanks for having me. And yeah, welcome to my talk about writing a kernel driver with Rust. So, yeah. Let me turn that off. So who am I? I'm Matthias. I'm 19 years old, and I'm a software developer. I really have a passion for developing and programming software. And I also like to explore new technologies on my own time. And that's also how I learned about Rust. And I also have an interest in software security. For example, obfuscation techniques, anti-debugging techniques, and antivirus, DRM, anti-cheats, and all that stuff is really interesting. So yeah, let's look at the agenda. We'll look into what exactly a kernel driver is, who uses a kernel driver, and how we can build our own kernel driver with Rust. And then also a short conclusion and a quick Q&A. All right, let's get started. So to be able to understand what a kernel driver is, we need to understand the difference between user mode and kernel mode. So in user mode, all your applications like Chrome, Word, or Discord run. And they can interact with the kernel, where the kernel drivers run. And the kernel drivers interact with the CPU, memory, or devices like the network card. And there's one important concept. The kernel has access to everything. So if you don't know what you're doing, you can easily crash and end up with this screen. So everybody has seen it. This is the blue screen. This happens, for example, if you corrupt critical data, or in this case, when a critical process dies. So the operating system can no longer be run safely. So we need to do a restart, and yeah. All right. And you can usually recognize kernel drivers with the .sys extension. Okay, who uses kernel drivers? So of course, first of all, antivirus software, because they can log much more data than in the user mode. And for example, can also register callbacks that notify them when a new process is created or when a DLL is injected somewhere. And they can prevent that and block that from happening. And they also have far more options to detect suspicious behavior. Then also anti-cheats or cheats. So anti-cheats in general want to protect a game, or more specifically, they want to protect the game's memory so it can't get edited. And if the anti-cheat runs in the user mode, they are very limited because they can easily be circumvented if you develop your own kernel driver, because the kernel driver has access to everything. And yeah, then there's also the NSA or hackers or malware developers in general. So there's rootkits or bootkits, and they are very hard to detect because they have access to everything. So they can also easily achieve persistence by, for example, rewriting the master boot record or doing some other tricky stuff. And often in the kernel, there's often many techniques that are not known. So there's lots of potential for abuse. Luckily, Microsoft knows this and decided to implement some protection for that. For example, PatchGuard will look for suspicious behavior. For example, Windows has internally a linked list with all the processes. And if for whatever reason a process is not in the linked list, then the system will just crash with a blue screen, because it obviously shouldn't ever happen. And there's also newer, more secure techniques like virtualization-based security, which uses a hypervisor and is even harder to circumvent. And also companies like NVIDIA, AMD, or any other company that needs to have access to the hardware. And yeah, for example, also network drivers also use kernel drivers. Okay, let's get into the how. How can we implement our own kernel driver? So the first thing we want to do is create a new project. We can use Cargo for that, like Rainer showed us in a previous talk. And we create a new binary crate called driver. All right. So a normal Rust application would look somewhat like this. But obviously, this doesn't work yet and can't be run in the kernel. So we need to adjust it. So the first thing we should do is remove the standard library, because the standard library provides lots of abstractions. For example, printing to the console. But if we try to build the project now, we get an error. Panic handler, function required, but not found. Okay, let's implement it ourselves. So now we added a new function called panic, and we get a panic invoice parameter. And this is pretty simple. Whenever our program panics, crashes, normally the standard library implements panic handler on its own. So if we crash in the user mode, there will be a nice error message and stack trace printed into the console. But in the kernel, there's no console, so we can't do that, and we have to implement it ourselves. So here we can notice the exclamation mark. This just means that this function does not return. And we can just place an infinite loop there, and this will not yet compile, but Rust will be satisfied. All right, the next thing we need to do is create our own entry point, because normally we have the C runtime, which gets called before our actual main entry point. But in the kernel, driver entry, our new function, is the first thing that gets called. So we name it driver entry because that's usually the name in the kernel, so we stick with that. Then we adjust the return value to an unsigned 32-bit integer, and we return 0, which stands for status success. Then we also use the correct application binary interface with the external system. This just makes sure that LLVM and Rust so that the correct registers are used for the return value and parameters. And then the no mangle just makes sure that Rust does not modify the function name in the binary. All right, so we also need to adjust the crate type in our cargo.toml, because kernel drivers are actually kind of similar to dynamic link libraries, DLLs. And the only difference there is they use different imports. So we can just rename our main.rs to lib.rs and adjust the crate type to cdylib. One important thing here is don't use dylib. Dylib is used for Rust libraries, and this includes lots of metadata. So if you want a large driver, then you can use dylib, but in general, you don't want to use it. So we'll just use cdylib, which removes the metadata. I actually stumbled upon this because I was wondering why my Hello World kernel driver has 180 kilobytes. And until I found that out, it was actually 5 kilobytes large. All right, so if we want to compile the program, it still doesn't yet work. We need to adjust the linker settings. So in Rust, we can specify a cargo.config. And we specify the target, in my case, Windows MSVC. And then we have pre-link and post-link args. The most important ones here are entry in the post-link args, the second one, where we specify our function we created. This is the first thing that gets called. And in the pre-link args, we specify /driver to make sure that we actually build a Windows kernel driver. All right, so now we should be able to compile the project, but we can't yet use any kernel APIs. For that, we need to tell the linker where all the libraries are. So this, you don't have to look at all the code. This basically does the following. So we look up the path to the Windows kernel driver kit. This is done via the registry, but that's not important right now. Then we select the correct platform, for example, 64-bit or 32-bit. And then we just specify it with the cargo Rust C link search native and print it to the console. And if we do that in the build script, Rust will automatically search in the following directories. So we should now be able to call kernel APIs. So in this case, we have to define the function ourselves. So I'm using is address valid. This basically checks if the passed virtual address, if a page fault will occur. So a page fault is basically when the address cannot be accessed. So if the address is valid, this should return true because a page fault will not occur. And I also specified the type pvoid because in Windows, that's usually used for addresses, and it makes it easier to copy paste the definitions from MSDN. All right, so now we can use the function. We obviously have to wrap it into an unsafe because Rust cannot verify that this function is actually there. And we can just pass 0. And then we can print it. I created a log macro, which we'll see in the next slide. And then we print it. All right, so the log macro looks like this. We are using another kernel function called debug print. This is similar to printf, but prints to the kernel output. And there's two versions of it. The first one is we just print a string. And the second one is we print a string with arguments. Then we also use the concat macro to add a prefix and the postfix, the null terminator, which is in this case really important because, as you probably know, C and C++ have a null terminator at the end of every string so that they know where the string ends. And yeah, and if you look at this example, you might already see a security vulnerability because in this case, we can pass any arguments. So if you go back to the previous slide, for example, we could specify %i, but don't pass is valid. So we would print the string, and debug print would look in the stack and check and just take the next variable that's there and print it onto the console. And this can be quite serious vulnerability and can be abused. Obviously, in our case, not, but if you have user input, then it can be abused. Okay, let's look at a comparison between Rust and C or C++. So you might have a function like this in C. The function is named do something. We get a process ID, and then we look up the process by a process ID. And the output parameter is the PE process structure, a pointer to the E process structure. And then we check if it's successful. If it's not, we return false. And then you can already see an important thing. We have two conditions there. And in both conditions, we return. So we have to dereference the object before we return, because internally a reference counter is added. So we need to subtract one from that via the dereference object function. And at the end, we need to do that too. But you can imagine if you don't watch out, you can easily forget it and potentially leak memory in some other cases. All right, how could we do that in Rust? So first of all, I would create a process structure. And internally, we just store the pointer to the eProcess structure. And then we can create a new function called byId and pass the process ID. Then, as before, we look up the process, check if it's successful. And here comes an important feature of Rust. We can return some if we actually got something and none if it failed. So no more null pointers in Rust, which is awesome. So here comes the most important thing of Rust. In Rust, there's this trait called drop. This gets always called whenever the object goes out of scope. So in our case, we check if the process is not null, and if it's not null, we can dereference the object. So if we take the previous function and rewrite it in Rust, it will look like this. So it already looks a lot simpler. So first we create a new process structure. This is our process, not the PE process structure. And then at the end, we have the question mark operator. This basically says if byId returns none, return from this function and return also none. But if it returns some with the process object, then just unwrap that and store it in the process variable. And then we can just do the conditions, and we basically don't have to care about deallocation or other stuff. And then we can return again, and when the function returns, drop gets called and calls the dereference object function, which is awesome because Rust does this automatically. We don't have to do it ourselves. So no more errors, no more human errors. All right, here comes a kind of tricky topic, Unicode strings, because in the kernel, almost every function that has a string as parameter uses Unicode strings. And Unicode strings are special because they're not 1 byte, but actually 2 bytes. And Windows also has a special structure called Unicode string, all in uppercase. And in order to pass our own Unicode string to a Windows kernel function, we need to first convert it. And in the kernel, you don't have access to the standard library. So you can't just make an iterator over a normal string, convert it into U16, and then collect it into a vec, because a vector is not available in kernel because you don't have access to the standard library. So I found this cool crate that does this for us. So it's called offstring, and there's the wide macro. And this macro basically returns a slice of unsigned 16-bit integers. And 16-bit integers are 2 bytes wide. And then we can just create our own Unicode structure, Unicode string structure. And there's also a Windows kernel API for that. But in my opinion, we can just do it ourselves because we can't make any mistakes if we do it ourselves. And yeah, so we just get the length, then get the character count. And Windows is kind of weird. So we have the length and the maximum length. Length is actually the length without the null character. and maximum length is the length with the null character. And then we just store a pointer to the string in the buffer. All right, so what if we wanted to use STD features like vector, hash map, or string, or other stuff? So we can actually create our own allocator. So we can use vector in the kernel.
Matthias, do you have a technical problem?
Yeah, my headphones turned off.
Yeah, okay, it's fine. Sorry.
Okay.
Go on.
So yeah, so we can actually implement our own allocator. And we do that by using the global alloc trait. So we have our own struct called kernel alloc, and then we implement the global alloc trait. And we have to implement two functions, alloc and dealloc. And they're pretty straightforward. We just allocate a pool in the alloc and free it in the dealloc. And also a alloc error handler. This is just important if we ran out of memory, but yeah. Okay. Let's look at Rust Puncheon. If you don't know Rust Puncheon, this is a tool that allows to automatically generate Rust bindings to C or C++. But in some cases, it can get quite weird. So for example, in this example, we have a physical address. We initialize it with std mem0. Oh, that should be core mem0. And then we get access to the quad part. You might now think this is weird. Why do we have to get quad part underscore mute? Why do we have to call the function? And why can we only then modify the quad part variable? Well, if you look at the C bindings behind it, you'll see this. A physical address is a large integer. In the large integer, oh, it's a union. So this is a disadvantage of Rust, because Rust actually has a union, but you shouldn't use it. And a union, if you don't know it, it basically says the quad part is an int 64, so it's 8 bytes on 64-bit machines. And then we also have the struct with the low part and high part, which are ulong and long, which are both 4 bytes. So together they are also 8 bytes. And union says we can either access the struct or the quad part. So they both point to the same memory, and we can modify it if we want. So we don't have to do some bit shifting and stuff, which is pretty cool, but can also be really dangerous. So yeah, that's the downside of Rust Puncheon. Okay, let's come to another downside. So unsafe. You obviously shouldn't use unsafe, but here's a project, kernel driver written in Rust, and it's actually generated with Tokay, which is also a tool written in Rust, which counts statistics of projects. For example, lines of code written. And we can see in total, I've written about 3,700 lines of Rust code. And in this code, I've used 205 unsafe blocks, because in the kernel, you can't really do anything without the standard library. You have to access Windows kernel functions. So if I already implemented lots of abstractions, so I don't have to call unsafe over and over again. But all the functions also return raw pointers, which are obviously unsafe. So yeah. And yeah, let's come to raw pointers. So for example, in a normal Rust application, you could have something like this. You store a raw pointer in the variable something. And obviously you have to check whether the pointer is null, because when you use it later, you can crash. So we check it with an if something is null, and then maybe return or do something else. And then later use it with the function foo. So this is really a lot of code just for a pointer validation. So we can use traits and optimize it. So first of all, create a new trait called pointer validity. And we create a function in there called valid, and it captures self and return an option of self. And we also need to specify that self is sized, because we capture the variable and return it again. Now, so we can implement it for both mutable pointers, but also constant pointers. So this will look like this. So we have impl t, so it's generic. For every mutable pointer, we implement this trait. So, and in this function, we just check if self is null, is not null, we return sum of self. And if it's null, we return none. And now we can actually do something like this. We can use the question mark operator again. And for example, in most cases, you want to return out of the function. And this makes the code really clean and simple. And then we can use it in foo again. All right. Now, should I use Rust when writing a kernel driver? This is a hard question. Let's look at the pros and cons. So obviously the cons. There's no official bindings yet, because I doubt anyone's using kernel drivers in production or somewhere. So there's some bindings for it, but they're very incomplete, and you have to implement all the functions yourself, declare the functions yourself, like we did with the is address valid, which can also be tedious, because you have to go on the internet and look up the function definition, convert it to Rust. And if you're using undocumented stuff, this can be even harder. And yeah, Puncheon isn't perfect. I have had another example in the project I mentioned, where Puncheon, for whatever reason, generated some kind of anon gen1 variable. I don't know why it exists, but it's, yeah, that's it. And Unicode Strings. If you don't have a util function, util module or something that automatically converts your Rust string slices into Unicode strings, it's really tedious. And also lots of raw pointers, which can lead to vulnerabilities, crashes and stuff, and you obviously need to use unsafe for them. But there's also pros. So Rust does a lot of stuff at compile time. So obviously there's fewer crashes. And when you crash, when you have a blue screen, the entire operating system shuts down. And until it restarts, it can take some time. So this is obviously also a speed up in the development. And we can create a custom allocator. And then we can use stuff from the standard library. And as far as I know, C++ has no way to do that. So you can't just use any C++ type from the standard library in the kernel, which is obviously a downside, because you don't want to implement it yourself, because it can error prone. And then many people can decide they create their own implementation. Then you have then you can use many of these implementations, and you have to look at them and select the best one. So yeah, custom allocator is a pretty big point, and I'm really glad that Rust has this feature. Then also drop. you now don't have to care about deallocation anymore, which makes life a lot simpler. And option and result. So no more null pointers, and yeah, it's pretty cool. And also crates.io and docs.rs. So right now, there aren't really many crates you can use in the kernel because the ecosystem is just not there. Yeah, obviously you can use crates that have no STD support. For example, Serde. The deserialization and serialization library has no STD support, which is pretty cool. So you could interact with the user mode and the kernel mode driver via JSON, for example, and also docs.rs, which allows you to host your documentation for these crates. And in general, the entire Rust ecosystem, the Rust toolchain, because Cargo, you can simply build it with Cargo, which is also pretty nice. You don't need any other tools. It just works. And yeah, are there any questions?
Matthias, first, let me say thank you for the presentation. It's really awesome. I know you are rather fresh from school and you did a great job. It was really interesting. And yeah, congratulations for this really interesting topic. Yes, we have a bunch of questions. In your slides, we saw the Win API, and we have a question. Does the Win API abstract kernel space APIs in Windows, or can you elaborate a little bit what this use Win API does and what it is?
I hope this one it is.
Yes, it is an example. Yep.
Okay. So in general, Windows. So this is just the definition of the Unicode string structure. And in Windows, you can use it both in the kernel, but also in the user mode. So there's this Win API create, and in the shared module, that's all the stuff you can use in the kernel and in the user mode. But you cannot use, for example, what's a user mode function? For example, create process, because it simply does not exist in the kernel. And if you try to call it in the kernel driver, you'll get a linker error because it cannot find the library for that. I hope that's answered the question.
I guess so. We will get a follow-up question if it didn't. One thing, a question from my side, I would be curious. During your research for this whole project of writing a kernel driver in Rust, I guess you looked through the internet. Did you find any clues about more or less official statements, for instance, from Microsoft, that they are planning or going to release better Rust support for, let's say, system level programming in Windows or something like this? Did you find anything in that direction?
So I have not seen anything where they mentioned specifically that they want to use it for kernel drivers in general or release crates with bindings for it. But I've seen some statements where they talked about that they want to use Rust more or want to begin using Rust side to side next to C++.
Yeah, maybe then we will get better libraries and better support on the Rust side. We'll see. The next question is a question somebody, Christian, was curious. It's not just Rust related, but generally, while you were developing your kernel driver, how did you test this kernel driver? I mean, I guess there are a lot of people, including me in this talk, who have never written a kernel driver. Is it just like pressing debugger start and you can debug your stuff and set breakpoints, or how does that feel? How does that look like?
So it's actually not that simple. So I've actually skipped part of that in my blog. You can read about it if you want. I also added a section where I created a build script which builds the kernel driver. But you can't just click on run and the kernel driver runs. You have to either manually use a tool and start it, or I guess you could also write a script for that, but you also have to start your IDE always as administrator because yeah, you need administrator rights to start the kernel driver,
Mhm.
and you also in Windows you have to enable a specific mode. It's called test mode, where some stuff is disabled, because otherwise you can't load your own kernel driver, because you need to buy a certificate and sign it and all that stuff. And then, so I was using a virtual machine. Then you can just copy the driver file there, run it, and there's another tool called debug view, which you have opened opened in the VM, and there you can see all the kernel outputs. There's also debuggers, but they're not really built into the IDE. So yeah, it's a lot more work than just a regular user mode application.
Okay, thank you very much. I just saw that the speaker from last time sent a bunch of informations about how to debug it with QEMU. I'm not sure, I'm not familiar with this technology. I'm not sure if I'm pronouncing it correct, but everybody who is interested might take a look at our Discord server, and there are some tips going on here. Also, Harald is mentioning that in Linux there are efforts to support Rust, but he guesses this will also take a while, and he mentions an article that you can follow along if you want to read more. You mentioned a sample that you have written. Can you please, after your talk, if that's possible, maybe you share a link to a blog or post, or maybe a GitHub repository, so that people who are interested can take a look at the entire working sample, and and maybe get some additional learnings from the work that you did.
Mhm.
Christian, again, a testing related question. That's an interesting one, and I'm really looking forward to your answer. Is there any way of doing things like automated testing or unit testing, code like that? How do you approach that?
So I was actually wondering in the early development of the kernel driver, I was wondering if that's possible, and I couldn't find a simple way of doing that without implementing everything myself.
Okay.
So yeah, that's an obvious downside.
Yeah. Okay, thank you. We have another question coming in. There was a slide about driver entry.
Oh yeah.
Yeah, and I think Mikkel is the name. He asked, he is a little bit confused. What was the system for the pub extern?
So there's different APIs, application binary interfaces, and this this basically tells the compiler, in our case Rust uses LLVM, that certain registers should be used for something. So in Windows, parameters are always in RCX, RDX, R8, R9, and then on the stack and so on. And the return value is always in the RAX register. And if you change the extern and then the application binary interface, you can tell basically LLVM that you want a different system. For example, does std call or this call? I'm not sure if this call is supported, but their EasyX always stores a pointer to the current object. And so, yeah, it's basically a flag for LLVM, as far as I know.
I see. Okay, I hope that clarifies the question. If not, let a follow-up question come along, please. So, a question from Christian. He's obviously not that into kernel development like I am. So he asked, did you see a lot of blue screens during debugging and testing, or what were your experiences here?
Yeah, especially in the beginning, because I made a mistake because, for example, there's a function called getSystemRoutineAddress. This returns a pointer to a certain function. And obviously pointers are unsafe. And when you incorrectly dereference it or dereference it one too often or one too less, you get a page fault and then a blue screen. So yeah, definitely in the beginning, I had a lot of blue screens.
I really can imagine that. I already see people discussing calling conventions and things like that. Matthias, if you have time and if you want, it would be great after this talk that you join us on the Discord server. Maybe people have additional questions, and if you can jump in and add your views to the discussion and maybe provide some answers, that is really great. Let me close today's meetup by saying again, thank you very much for this very interesting talk. Just like with the first talk, we will take this video and cut it in the next few days and put it on the official Rust channel. So with that, I check for the last time if we have any additional questions. Let me see. No, all the chats are. Yeah, people say thank you. It was very interesting. I would like to relay that comment onto you. And with that, I say thank you very much for the presentation of today. Thank you. So with that, I think we are done. Thank you very much for coming to today's Rust meetup. The next meetup will be somewhere at the beginning of November. I think we haven't fixed a date yet. It will be announced on rust-linz.at, so please check it out. We will also publish the date on our Meetup channel, and we hope that many of you will join us again at the beginning of November, and when we have, hopefully, a lot of interesting speakers. We have some really interesting discussions going on. So thank you very much, and enjoy the rest of the evening. See you on Discord. Bye.